Hello and welcome to this A-level chemistry video about acylation. In this video, I'll start by looking at acyl chlorides and acid anhydrides, which are the chemicals required for acylation. We'll spend the majority of this video focusing on the mechanism of nucleophilic addition-elimination and also the equations for the reactions. Acylation is a very common step in an organic synthesis, and it involves the addition of an acyl group to a molecule. And an acyl group typically looks like this, where we've got a carbonyl group connected to some kind of carbon chain, which could be any length. This is an important step in many industrial processes, for instance in the production of drugs such as aspirin. It's likely for your assessed practical work, such as one of the required practicals, that you might be required to carry out the acylation as part of a preparation of an organic substance. The two most common ways of introducing an acyl group into a molecule are using a reagent that is either an acyl chloride or an acid anhydride. It's highly likely when doing acylation in an exam that you'll be asked about one of these two organic molecules, but in theory it could be any organic molecule with an acyl chloride group somewhere as a part of it. Acyl chlorides have the functional group COCl, which contains a double bond between the carbon and the oxygen, so effectively a carbonyl group, and there is a chlorine attached to the carbonyl carbon, which makes this a different functional group to a normal carbonyl group. When we name acyl chlorides, we need to first determine the carbon chain length. And so in this example that I've got here, we've got 3 carbon atoms, so this is prop-an, and all acyl chlorides end in the same way with oil chloride. And so this would be propanoyl chloride. We might prefer to use acyl chlorides in the acylation mechanism because they react very quickly, which means that they will be able to produce acyl derivatives such as esters very easily. However, their reactions are very violent, which makes them difficult to control, and they also produce HCl as a byproduct, which means there'll be fumes of a toxic gas being produced, which is why we sometimes prefer to use acid anhydrides instead. Acid anhydrides are comprised of 2 identical carboxylic acid molecules. These have joined together through one of the singly bonded oxygens in an OH group, and the H from this OH group and all of the other OH group in the other carboxylic acid have joined together to combine to form water in a condensation reaction. And so we produce the acid anhydride and water when these 2 carboxylic acids come together. We take the name for the acid anhydride from the carboxylic acids from which they were made. So when you name them, you simply remove the acid part of the name for the acid and replace it with anhydride. And so if this was 2 ethanoic acids that combine together, we would produce ethanoic anhydride. In industry, it's usually preferred to do acylation using an acid anhydride since they are cheaper and less corrosive than acyl chlorides. Additionally, they have less vigorous reactions than acyl chlorides. They will react much more slowly. And also they will only produce carboxylic acids as a byproduct. And for these reasons, they are much easier to control when carrying out an acylation reaction, and they are much safer, all of which makes them preferable to acyl chloride reactions. The nucleophilic addition-elimination mechanism occurs when there is a reaction of the carbonyl group in one of a number of chemicals, and these are acyl chlorides, where there is a chlorine attached to a carbonyl group, acid anhydrides, where there is a second carbonyl group connected to the first by a bridging oxygen atom, and an ester, which has got the carbonyl group connected to an oxygen and then a carbon chain. You can recognise that a nucleophilic addition-elimination mechanism will occur when you see that it's a reaction of the carbonyl group in one of these 3 chemicals. What actually happens in a nucleophilic addition-elimination mechanism is a positive-seeking substance, the nucleophile, attacks and joins onto the carbonyl carbon atom, which will be electron deficient. And so this is the addition stage of the mechanism. And then the elimination stage of the mechanism is where part of the original organic molecule then leaves. This mechanism occurs because the carbon in the carbonyl group is electron deficient. And this is because it's actually connected to two electronegative atoms, the oxygen and sometimes another oxygen or a chlorine. Both of these atoms are more electronegative than the carbon, so they pull the electron density from the covalent bond towards themselves, leaving the carbon delta plus and the oxygen and the chlorine delta minus. And so the nucleophile attacks the carbonyl carbon and forms a new bond to it. As well as knowing which organic molecules will undergo nucleophilic addition-elimination, you can also recognise that this mechanism might occur depending on the nucleophile. There are four that you need to know about. First of all, we've got ammonia, which has got the lone pair on the nitrogen, which enables this to act as a nucleophile. We've also got amines, which also contain nitrogen, and we can have a carbon group of any different length. And then we've got water, which has got the oxygen, which has got the lone pair that enables this to act as a nucleophile. And then we have alcohols last of all. Normally, we would see methanol as the nucleophile. There are so many different nucleophiles that can take part in nucleophilic addition-elimination and a number of different organic molecules that they can attack. So what we're going to do is we're going to look at an overview of the process first by looking at, in general, how nucleophiles might attack an acyl chloride or acid anhydride. And this generalization is useful because all of the nucleophilic addition-elimination mechanisms occur in the same way. If I generalise and I use my acyl chloride or acid anhydride or my ester represented in this way, where we've got the carbonyl group and the carbon chain, and we've got L representing the rest of the molecule, which might be a chlorine, it might be an OCH3, or it might be the rest of an acid anhydride. This together is generalised and referred to as a leaving group, so I'm giving it the symbol L. The nucleophile that could attack this compound will always have at least one hydrogen atom in it, so I'm going to use nuc to represent the nucleophile, but I'm also going to show one of the hydrogens for a reason that will become clear. The nucleophile must also have a lone pair on it, which will donate in the reaction, so I'm showing that lone pair as well. The first stage of the nucleophilic addition-elimination mechanism is the formation of a new bond between the nucleophile and the carbonyl carbon. The nucleophile is positive-seeking and it is attracted to the electron-deficient carbon, and so it forms a new bond to it. This would give that carbon atom 5 bonds, and it can only have 4, so 2 of the 4 electrons in the carbonyl double bond are pushed towards the oxygen, and so that double bond effectively breaks and becomes a single bond. This organic starting material that would have been trigonal planar around that carbonyl carbon has now been converted into a tetrahedral intermediate substance. And you can see that we've got the nucleophile now connected to the carbonyl carbon. We've got now a single bond between the carbon and the oxygen that it was doubly bonded to. And we've now got a lone pair on that oxygen, which we need to show, because that represents 2 of the electrons that were in the double bond that oxygen now has sole ownership of. As a result of it taking those 2 electrons away from the double bond, it will now have a negative charge, and it's really important that we show that negative charge. In addition to this, the nucleophile has donated its lone pair of electrons to the carbonyl carbon, and so now it will carry a positive charge, and we need to show that on the nucleophile. And so what we've got is our tetrahedral intermediate, which we do show as being planar, being flat, just because it's easier to draw this way, but it is tetrahedral, and we've got a positive charge and a negative charge within it. This then moves us on to the elimination step of nucleophilic addition-elimination, because three things happen all at once. The lone pair on the oxygen goes back into where it was the double bond, and a new bond forms between that carbon and the oxygen, and we now get our double bond back again. That would give the carbon 5 bonds again, but what happens instead is the bond between the carbon and the leaving group breaks, and the leaving group, whatever it might be, takes the pair of electrons from that bond and has them for itself. And then the nucleophile, which was positively charged, takes a pair of electrons from the bond inside what was the original nucleophile, and part of that nucleophile takes that pair of electrons and brings it towards itself, and the hydrogen that was in the bond within that nucleophile is now leaves, and we get what's referred to sometimes as deprotonation occurring as a result of this bond breaking. And so at the end of the reaction, we've got our acyl group with the majority of the nucleophile now attached to it. And then we've got our leaving group, which would be negatively charged and have a lone pair of electrons, and we've got the hydrogen that was lost as a result of the deprotonation. These two ions would come together and produce a separate molecule, which would be the byproduct. This is my preferred way of showing nucleophilic addition-elimination mechanisms, but there is an alternative which takes place over 3 stages. The first stage is identical because we have the addition part of the mechanism where the nucleophile attacks the carbonyl-carbon and the double bond partially breaks. Then elimination occurs in its own step where the oxygen reforms the double bond to the carbon and the leaving group leaves, taking that pair of electrons with it, so it is eliminated from the molecule. But the deprotonation occurs in a separate step. So we've got our organic intermediate here, which has still got a positive charge on the nucleophile, and so what happens in this stage is the bond between the nucleophile and the hydrogen breaks, the nucleophile takes both of the electrons from the bond, and the hydrogen leaves as an H+, and again we'll end up at the same product, but this has just taken place over an extra step. And so for me, I prefer to do it over just 2 steps because I think this makes life easier and I think it takes less time. This mechanism has a lot in common with nucleophilic addition, unsurprisingly because of its name. Nucleophilic addition also in stage 1 has the exact same curly arrows. The difference between addition and addition-elimination occurs where the nucleophile in addition is always going to be negatively charged, and so that means the intermediate in nucleophilic addition will always simply have the 1 charge of being negative on the oxygen. And so the intermediate is nearly the same as well, but not quite because you won't have this positive charge on the intermediate. And then the elimination part of the mechanism has a lot in common with simple elimination, and the biggest similarity is the number of curly arrows for my elimination here is 3 in my step 2 for my top mechanism, and in regular elimination from alcohols or halogenoalkanes, the elimination step there also has 3 curly arrows in it. Acyl chlorides react vigorously at room temperature with ammonia. And so if I had methanol chloride reacting with ammonia, the first step of the mechanism would be the ammonia donates its lone pair to form a new bond to the carbonyl carbon that it was attracted to because that carbon was electron deficient. And then the oxygen takes 2 of the 4 electrons from the double bond that it shared with that carbon atom, and this produces our intermediate, which has got the nucleophile now connected to the carbonyl carbon, and the nucleophile will be positively charged because it's used its lone pair to form a new bond. The oxygen that was part of the carbonyl group originally is now going to be negatively charged because it took 2 electrons out of that double bond, and it needs to be shown as a separate lone pair now on the oxygen. And then I'm showing one of the bonds between the nitrogen and the hydrogen as being separate, and I'm showing it on display because what's going to happen now is that bond is going to break and the nitrogen is going to take both of the electrons from the pair. You can see that I've drawn my nitrogen and hydrogen quite close together, so I'm exaggerating this curly arrow to make it really obvious that it's starting from the bond and finishing on the nitrogen atom. In addition, we remake our carbonyl double bond because that lone pair goes back into the area between the carbon and the oxygen, and we get a new bond forming, and the chlorine takes the electrons from the bond that it shared with the carbon, and that leaves and it is eliminated along with the hydrogen. And so the HCl is eliminated from this molecule. And then the acyl chloride derivative produced in this instance would be an amide, because the ammonia has formed on the same carbon as the carbonyl group, and so we've now got a carbonyl group and an NH2 on the same carbon, and this is the amide functional group. And you name amides by simply having methan, ethan, propan in front of it. And so since I was using methanol chloride in my example here, I would produce methanamide. And we can use an equation to represent this reaction as well as a mechanism. And so this is the structural formula of methanol chloride, and it's reacting with ammonia, and we produce our methanamide, and the HCl is eliminated, and we would observe misty fumes. And with acyl chlorides, the second product is always HCl, so we would always observe these misty fumes of the toxic HCl gas. Acyl chlorides also react vigorously at room temperature with primary amines, and the mechanism is identical to when ammonia reacts, but we produce something different in this case. And so the first step is the attack of the nucleophile on the carbonyl carbon. That lone pair forms a new bond between the nitrogen and the carbon, and the bond between the carbon and the oxygen partially breaks, with the oxygen taking both electrons from the bond. Then we produce our intermediate, which needs to have a negative charge on the oxygen and that lone pair, and the nucleophile is now attached to the carbonyl carbon, but it will be positively charged because it's used its lone pair to form this new bond. And so in stage 2, the bond between the carbon and the chlorine breaks and the chlorine leaves, and the oxygen uses that lone pair to remake the bond between the carbon and the oxygen, and that now becomes a double bond again. And from within the part of the molecule that was the original nucleophile, the positive charge is stabilized because the nitrogen takes the pair of electrons from the bond that it shared with that hydrogen, and the hydrogen is eliminated as an H+ ion. And so we produce this organic product, which would be referred to as an N-substituted amide on this occasion. And so it's called this because we've got something that looks really similar to an amide. If this CH3 group wasn't there and was an additional hydrogen instead, this would be an amide. But because we've got a methyl group, it needs to be a substituted amide. And because the methyl group is attached to the nitrogen, we use the nitrogen as a position indicator, just like we might say 1, 2, 3 in a complicated name. And so an N-substituted amide has got a carbon chain attached to the nitrogen. So in this case here, when we're naming our N-substituted amide, we should always name the amide part first. And so we've got a carbon chain of 2, so this would be ethanamide. But we've got a methyl group attached to the nitrogen as well, and so this would be N-methyl ethanamide. And remember, we make our two ions as a product, which would come together to make HCl. So we would refer to this as having eliminated HCl from the molecule. In terms of an equation, we've got our ethanol chloride structural formula here. It's reacting with the methyl amine, and we're producing our N-methyl ethanamide and the HCl. Acid anhydrides undergo the nucleophilic addition-elimination mechanism in the exact same way as acyl chlorides. Firstly, the nucleophile uses its lone pair to form a new bond with the carbonyl carbon, and it attacks it because the attraction is there between the partially positive carbon and the nucleophile. The electrons in the double bond are then taken partially by the oxygen, so that double bond is broken and becomes a single bond. This then gives us a charged intermediate with the nucleophile now attached to the carbonyl carbon and being positively charged because it's just used its lone pair to make a new bond. The oxygen, remember, is negatively charged, and we need to show that charge along with the lone pair that it's now got, having taken it from the carbonyl bond. That lone pair is then used to form a new bond between the carbon and the oxygen. We're reforming that double bond, and then the rest of the acid anhydride is now the leaving group, and so we've got a bond between the carbon and the oxygen which is going to break. The oxygen is going to take both of those electrons and leave this organic molecule. And the nucleophile part of the organic molecule needs to have its charge stabilized, and so that oxygen will take both of the electrons from one of the covalent bonds that it had, and it will take it from that hydrogen atom because that bond is easier to break, and so the hydrogen atom will also leave this molecule, and it will combine with the rest of the acid anhydride that left this molecule, and we will see the formation of a carboxylic acid. And in this case, because I was using ethanoic anhydride, we would produce ethanoic acid as a byproduct. The acyl derivative that we produce on this occasion, because I was using the alcohol methanol, would make an ester, and it would be a methyl ester because we've only got one carbon in the alcohol that attacked the ethanoic anhydride. And so this ester would be called methyl ethanoate. Remember, whenever you name an ester, you take the beginning of the name as how many carbons are in the alcohol, and the end of the name is to do with how many carbons are in the ethanoate or the propanoate part of the functional group. And as an equation, the structural formula of acid anhydrides looks a little bit odd. What we do is we show the part of the anhydride that is duplicated inside brackets with a 2 after it, and the oxygen, which effectively bridges these two groups together in the molecule, is shown outside those brackets. And so this is the structural formula of ethanoic anhydride. And then it's reacting with methanol, and we produce our ester, methyl ethanoate, and our ethanoic acid as our second product. Acyl chlorides react very vigorously with cold water, and the mechanism is nucleophilic addition-elimination. The water is the nucleophile, and it uses its lone pair to attack the carbonyl carbon and add on to this molecule. And the carbon has its bond that it's sharing with the oxygen partially broken. The oxygen takes both of those electrons from one of those bonds, and we end up producing an intermediate where we need to show that lone pair now on the oxygen instead of in that double bond, and the oxygen will be negatively charged. Additionally, the nucleophile has used its lone pair to make a new bond, so now it will be positively charged. What happens in stage 2 is the elimination. That double bond between the carbon and the oxygen reforms using the lone pair that the oxygen temporarily took out of the bond. Then the chlorine is going to leave, taking the pair of electrons that it was sharing the carbon away with it. The nucleophile needs to achieve stability, so it breaks its bond between the oxygen and one of the hydrogens and takes both of the electrons onto the oxygen, thereby stabilizing that positive charge, and the hydrogen leaves as a positive ion and the chlorine leaves as a negative ion, and so we end up producing hydrogen chloride, HCl, which we would observe as misty fumes during this reaction. The second product in this case would simply be a carboxylic acid. And since I've been showing methanol chloride at the beginning, the carboxylic acid that would be produced would be simply methanoic acid. And so the equation for this reaction would have methanol chloride reacting with water and producing methanoic acid and HCl. In summary, when carrying out acylation, you can use either an acyl chloride or an acid anhydride and you'll get the same acyl derivatives. But remember, the acyl chlorides are much more reactive. There are some common nucleophiles that you need to be aware of. If you used ammonia, we would produce an amide. If you used a primary amine, you would make an N-substituted amide. If you used an alcohol, you would produce an ester, and if you used water, you would produce a carboxylic acid. The only difference in the mechanism and the equation really is the byproduct, which could be HCl for the acyl chloride, or it could be a carboxylic acid if we'd been using an acid anhydride. So these are the most common nucleophiles that you're likely to encounter for this mechanism, but in theory, anything that's got an alcohol or amine functional group in it could react as well. And so this is particularly common in industry when making drugs such as aspirin, and so you need to be on the lookout for anything that might have an amine or an alcohol functional group. Okay, that's the end of this video. Thanks for listening.